We've been talking about different ways to determine the direction of forces and magnetic fields and the interaction between charged particles and magnetic fields. But now it's time to use some formulas to determine the amount of forces and magnetic fields. We'll start with this. The magnitude of a force felt by a charge moving through a magnetic field can be given by this formula. B is the magnetic field in Tesla. F is the magnetic force in newtons. Q is the charge in coulombs. And V is the velocity of the charge in meters per second. Sometimes you will see this equation written a little bit differently. If you rearrange it, you can say that the force, let me get my pen here, the force is equal to Q, V, B. The second formula is actually equivalent to the first. The force on a current-carrying conductor perpendicular to a magnetic field. The force on such a conductor would be equal to the magnetic field in Tesla times the current times the length of the wire. Now, something that's kind of interesting about these two formulas is that they are actually equivalent. If you take Q, that's charge in coulombs, velocity is speed in meters per second, and B is magnetic field in Tesla. You have Coulomb, meter, Tesla per second. Look at what happens here with our force on a wire. We end up with the same, basically the same thing. We've got magnetic field in Tesla. We've got current, which is coulombs per second, and then the length of the wire is meters. So we still have the same 3 units on top and seconds on the bottom. Let's try a couple of practice problems. Number 1, a thin 1 meter long copper rod has a mass of 50 grams. What is the minimum current needed to cause it to float in a magnetic field of 2 Tesla? The first thing that we're going to do is identify our variables. So we've got the length is 1 meter. We've got the magnetic field is 2 Tesla. And then giving us the mass of the rod is really a way to give us the force, because we're saying that there's going to be a magnetic force that's going to hold up the mass of the rod. So the force is going to be equal to 0.050 kilograms times 9.81. So we'll convert that to newtons. So our force is going to be equal to, 0.4905 newtons. Since we're dealing with a wire, we're going to use our second equation, which is that force equals BIL. And I'll simply plug in the numbers and solve it. So I've got 0.4905 equals the magnetic field times the unknown current times the length of the wire, which was 1 meter. When we solve this, we get that the current is 0.245 amps. Let's look at another one. Question 2. A proton moves eastward in the plane of Earth's magnetic equator so that the distance from the ground remains constant. What is the speed of the proton if Earth's magnetic field points north and has a magnitude of 5 × 10⁻⁵ Tesla? First, it's important to realize that if a proton is moving east-west and the magnetic field is running north-south, that the charged particle, the proton, is moving perpendicular to the magnetic field. That's really important because in order to get maximum force, you must have the particle motion and the field perpendicular to each other. If they're parallel, you'll have no force at all. Let's identify our variables. We've got the magnetic field of the Earth, the B field, is 5 times 10 to the 5th, or times 10 to the negative 5th Tesla. It looks like we don't have any other information here, but really we do, because they tell us this is a proton. So we know that the charge on the particle is 1.6 times 10 to the negative 19th coulombs. And what I'm looking for is the velocity of the proton. Again, what needs to happen here is the force. The magnetic force is going to hold up the proton. So the magnetic force has to balance out the weight of the proton. Now, the mass of a proton, and you can look this up on the green sheet, is 1.67 times 10 to the negative 27th kilograms. We would multiply that by 9.81 in order to solve for the force. Okay, so here we go. So we're going to say that the force is going to equal Q, B, B. So we would plug in our force, plug in our magnetic field, plug in Q, and then we could solve for the velocity. And I will give you a moment to do that. Okay, so we plug in our values, and I've done that down here. Plugged in my force, multiplied these numbers together to get 1.63 times 10 to the negative 26 newtons. Plug in the charge on a proton, the velocity is unknown, and then plug in the B field. And when I solve, I get a velocity of 0.002 meters per second. There's one more example that we need to do together. Actually, one more formula we need to talk about. And it's the magnetic field strength around a current carrying wire. Here, the B still means the magnetic field, the strength of the magnetic field in Tesla. Mu is the vacuum permeability. This is the same value we used with capacitors. It's 4 pi times 10 to the negative 7th Tesla meters per amp. We've got I is current in amps, and R is your distance from a wire. So what this allows us to do is it allows us to calculate the magnetic field strength based on the current and the distance from a wire. Let's look at an example. Find the magnetic field strength 10 centimeters from a wire carrying 2 amps. So let's look at what we've got here. We want the magnetic field. We've got the distance from the wire. I'll change this to meters right away, 0.10 meters. And we've got the current, 2 amps. So using the formula, B equals mu times I over 2 pi r. So I will plug in my values. Mu was 4 pi times 10 to the negative 7. The current is 2. And then in the denominator, I have 2 pi times the radius, which is 0.10. And we will take a minute to compute that. And we will get 4 times 10 to the negative 6 Tesla. Tesla are the units for the magnetic field.